This is Lesson 2, Improving Netbackup Performance. This is the second lesson in this course. In this lesson, we'll do an overview of Netbackup performance tuning. We'll discuss how to isolate and address bottlenecks. We'll discuss how to tune Netbackup buffers and how to tune Netbackup deduplication. And finally, we'll discuss using network resiliency to overcome communications problems. This is the Netbackup Performance Overview topic. When we approach the topic of performance tuning for Netbackup, it's important to have a set of clearly defined, realistic, and achievable performance goals in mind. And some very basic examples are shown on the slide here. I want to be able to get all of my backups done within the backup window. I want to minimize the footprint of backup activities on my client systems. And I want to reduce the time to recover data. So at a high level, those are very common performance goals. My performance strategies are the steps I'm going to take in order to achieve these goals. I'm going to look through the data path, and I'm going to analyze the entire data stream holistically, and I'm going to identify and troubleshoot bottlenecks in the data stream to try to optimize the flow of data from the client system all the way through to the target backup device. And I'm going to look for opportunities to tailor the backup method to the data type and possibly make use of features that Netbackup offers to improve performance. The first step in the performance tuning process is to identify bottlenecks in my data stream. And in order to do this, I have to take a high-level view of the entire path that my data has to take, beginning at the hard disk on the client system and identifying every interface that it has to pass through on its way through to the backup server and then eventually onto the target backup device. Every device that's involved, every interface that's involved, every network that's involved, all of these, basically every hoop that your data has to jump through on its way to its final destination is a potential bottleneck. And so the first thing I need to do is I need to determine my realistic throughput. And that is an estimate of the performance that I think I should be getting. And I'm going to look at each component I'm passing through and identify realistically its maximum throughput, and I'm going to look for the smallest number. Whichever device offers the smallest footprint is going to constrain the data flow. Now, I have achieved backup perfection, so to speak, when the rate limiting factor for my backups is the target backup device itself, where my tape or drives or my disk drives are spinning at their maximum possible speed, and every other conduit, en route from the client to that device has been optimized to get the data moving so that the target device is moving at its maximum speed. And so this slide here kind of shows an illustration of some of the hoops that my data jumps through, beginning at the client system, where I have to take the speed of the client disk into account, oftentimes a major bottleneck there, plus whatever processing the client is doing at the time of the backup, because this is usually a production server that I'm protecting. And then I'm going through some kind of a network to reach the Netbackup media server, and at that point the performance profile of the media server and how heavily it's loaded comes into play. And then I'm moving across usually a storage network, oftentimes a SAN, between the media server and my destination device. The destination device has some kind of interface associated with it that can handle a certain amount of data, and the tape or disk drive has a certain ingest rate, for how fast it can spin. And so I want to determine the realistic throughput of each of these devices and interfaces, and you'll notice I keep stressing the word realistic. And what I'm doing is I'm taking the maximum throughput that the vendor reports for this component, and I'm multiplying it by the real-world modifier. The real-world modifier, is of course a reminder that vendors test these devices under the most optimum, perfect conditions imaginable, situations that would be difficult or impossible to replicate in real life. So my real-world modifier is probably around 70 or 75%. For any given piece of hardware in your data center, if you can get 75% of what the vendor says is the theoretical maximum, you're probably doing pretty good. And so I'm going to go through, look at each one of these components, determine their maximum throughput. Now I mentioned that the vendor's spec sheets will help me out there. I can also get quite a bit of useful information in the Netbackup Planning and Performance Tuning Guide. And you'll see some samples of that on the slide here, where for network interfaces, for drive controllers, and for actual drives, we have listed here their theoretical amount of data that they can handle expressed in gigabytes per hour or megabytes per second. And so again, I'm looking here and I'm looking to identify what I should be getting. This amount of transfer is what should be possible. This slide shows an example of this process of analyzing my throughput. So I begin at the client systems, and based on testing that I've done, I feel that I've got two groups of clients here, one of which can give me an aggregate of about 400 megabytes per second in terms of throughput. Second group of clients, a little bit slower, I think they can give me an aggregate of about 300 megs per second between everybody in that second group of clients. And now let's trace the data path. As it leaves the clients, I'm hitting the network, and as in many cases, the network becomes a bottleneck, right? I'm using gigabit Ethernet in this example. I feel in my environment that I can rely upon about 90 megs per second of throughput, which is pretty good for Gig E, and so immediately I'm bottlenecking. Look at that top group of clients, 400 megs per second aggregate throughput gets reduced to 90 megs per second, because that's all the network can handle. But I have got 4 network interfaces in my media server, which is nice to try to keep this media server busy. So 4 times 90 megs per second is a total of 360 megs per second of data input to the media server. I then have to take a look at the performance profile of the media server and how busy it is doing other things. Can it handle this data rate at a sustained rate through the backup window? And let's just say for purposes of this example that it can. So then I'm going to have to go move stuff across the storage network to my actual backup devices. And I've got my SAN here, and it looks like I'm using a 4 gig fiber link that can move 400 megs per second. So okay, that's adequate to handle the amount of data that's moving. Now I've got a disk array that can write at about 200 megs per second. And I've got 3 tape drives here that are writing at about 144 megs per second each. So that's about, to me, I think that's about an LTO3 generation tape drive with compression. So you'll notice the total amount of speed I get from my backup devices exceeds the throughput of the SAN. Assuming that this is all just one fabric that we're talking about here, I'm bottlenecking on the storage side here. So immediately, just by going through and doing this, I've determined 2 possible areas of improvement. I know that I'm bottlenecking at the network level, and if I could go to 10 gig instead of 1 gig Ethernet, I'd be able to move more data to the media server. I'm bottlenecking again on the storage side. If I could have multiple fabrics, or if I could have a faster SAN, maybe go to 8 gig instead of 4, I would be able to improve backup performance. And again, my overall goal here is determine the maximum speed for my backup devices and do everything possible to keep them spinning at that maximum speed. Make sure every other conduit has been optimized to move that data right along. Now, of course, the easiest recommendation to make is, just replace your networks. Well, that costs money, right? So maybe it's not in the budget right now to replace my network from Gig E to 10 gig. The next thing I could start thinking about are there features in Netbackup that would decrease my network utilization and accomplish the same goal without costing me a lot of money. Maybe if my backup disk there is doing a deduplication, so it's an MSDP pool, maybe I can make use of client-side detup or a Netbackup accelerator. Both of those will decrease the amount of network space required and allow me to improve backup performance. This slide shows us some good common sense guidelines for doing throughput testing. Determining my maximum practical throughput, like we were talking about on the previous slides, and then testing it. I've determined that this is the amount of data I should be able to get based on the vendor's specs and my real-world modifier. So the next step is, am I getting it? In the PowerPoint world, this is what I think I should be able to get. Does my actual real-world performance match, the numbers that I put down in PowerPoint or Visio? And if not, why not? Here's where we look for bottlenecks that are impeding the throughput I think I ought to be getting. And as they recommend on the slide here, common sense guidelines. Test a large and identical chunk of data at a time when systems are otherwise quiet. Reset everything, expire media after every test. Document everything thoroughly. And if you're making changes, make one change at a time and test again so you can determine, what change you made had an effect on the overall performance. There are probably a number of different data collection points in your data center where you can get information about performance to see if you're getting the performance you think you should be getting. Some of them are within Netbackup, and some of them could involve the use of outside third-party tools. Here's an example of the kind of data you can get right from within Netbackup. And so in the job details, you see Netbackup's estimate in kilobytes per second of how fast a particular backup job ran. I see that in the activity monitor. I can also see that through Op Center. I can also see that from the command line using the BP error command or through the all log entries reports in the console. Here's an example of another utility that can be used from within Netbackup as a data collection point. This is NBPerfCheck, which measures the read speed and the write speed of a disk array. You can see sample syntax here for creating a test file on a disk and then reading back the test file. That's a good way of measuring the performance of a disk. It's commonly used with disks where you're doing deduplication. Note the recommendations here from Veritas that you work with support in interpreting the results, and the minimum disk performance level of 130 megs per second for deduplicated read and write operations. I cannot stress highly enough the importance of good throughput and fast-performing disks when it comes to build-it-yourself MSDP pools. Having disks that are not able to maintain at least a sustained 130 megs per second, and more would be better, results not only in problems with performance, but problems with reliability. If your disks can't sustain a certain amount of throughput, then you risk problems with data corruption. So definitely make sure if you're going down the MSDP route that you have fast-performing disks and a good connection to them. Consider the use of Netbackup appliances for MSDP, because one of the nice things about appliances, again, is that the disks have been robustly tested by Veritas to ensure that they have good sustained transfer rate, and you're not going to have issues with corruption. This is the isolating bottlenecks topic. Continuing our conversation about troubleshooting the data stream, we've gone through and we've determined our maximum theoretical throughput. We've done some testing, and we've determined that we're not getting the performance that we were expecting. And so the next question we're asking is why? I've got a bottleneck somewhere, so what am I going to do to try to identify where that bottleneck is and correct it? And so I need to collect as much information as I can. So these bottlenecks that I'm getting, what do we have in common here? Is it the same clients that are affected? Are they the same major application? Or are they the same operating system? Or the same network segment? Are they all going to the same backup server or to different servers? Are they all going to the same storage unit or to different storage units? And is this always been a problem? Or is this something new that's only recently cropped up? And if it's something new, what's changed that might have affected it? The article mentioned here, Tech 147296, gives an excellent overview of Netbackup performance testing. There are other utilities that are available, such as NBSU, the Netbackup support utility, and this is a script that is shipped with the product. It's in the support directory, and it can be used to probe your environment to look for environmental variables outside of Netbackup that might be affecting and degrading backup performance. As part of the process of identifying where my bottlenecks are located, I'm going to take a look at the information in Netbackup reports and log files to try to identify if the bottleneck is happening on the producer side or the consumer side. And here's what I mean by those terms. In any kind of an operation, a backup or a restore, we have one system that is the producer, that is sending the data, and another side which is the consumer, which is receiving the data. And the reason why we use generic terms like that is because it's dependent upon the type of operation we're doing. In the example you see here on the slide, we're talking about a backup operation. So in a backup operation, the client system is the producer. the NetBackup client process, BPBICR, on the client is sending the data. And then it's going across the network to the NetBackup media server, and the NetBackup media server is the consumer of this data. Ultimately, the BPTM, the NetBackup tape manager process, receives this data, puts it in shared memory on the media server, and then a second copy of the BPTM process actually writes that data to tape or to disk. And you can see here that the size and the number of shared memory buffers can vary depending on NetBackup version and what platform you're running on. In this example here, we're using 8 data buffers, 64 kilobytes in size. That number can be adjusted and tuned as part of the performance tuning process, and we'll talk about that later on in this lesson. But what we can do is we can look at the output of the BPBICR process and the BPTM process, and we can try to look for waits and delays to be able to identify where is this bottleneck. Is it on the producer side, i.e. the client, or is it on the consumer side, i.e. the media server? Here's an example of a restore operation where we see that the roles have been reversed. The BPTM process on the media server is now the producer of the data, and the TAR process on the client system is now the consumer of the data. And again, although the terms have switched, it's still the same sort of thing we're looking to do here, identify where the bottlenecks are located. Do I have a consumer side bottleneck, i.e. the client, or do I have a producer side bottleneck, i.e. the media server? Here's an example of looking at the output of NetBackup reports to be able to identify where the bottleneck is. In this example, we're talking about a backup operation where the client is the producer and where the media server is the consumer. And in this case, it is the consumer process, the BPTM process on the media server, that's complaining about delays. And here's what's happening. The client is sending data to the media server, and the data is going into shared memory buffers on the media server. The BPTM process is then reading that data out of the buffers and running it to tape in this example. And the BPTM process on the media server is writing the data faster than it's coming in. And so eventually the shared buffers are empty and the BPTM process has nothing to write because it's just, data's not coming in fast enough from the client system. At that point, when the BPTM process has to stop writing because it ran out of stuff to write, it's going to start complaining about it in the logs. And so I'm going to see waits and delays listed. A wait is a time during the backup that the process of writing data had to stop, and a delay is the length of time it had to stop for. And so you see these messages in the NetBackup activity monitor, and when you're interpreting them, it is the waits that you should be concerned about, not so much the delays. Because if you actually do the math, each delay is about 30 milliseconds in length. The total amount of time that you were stopped for often isn't that long. It's the fact that you had to stop. It's the fact that the backup operation had to completely pause and wait around for data to come in. And so excessive numbers of waits on the consumer side indicate a slow data stream coming in from the client system. On this slide, you see an example of the exact opposite problem. Now again, it's a backup operation, but this time we're seeing complaints in the BPBICR process on the client. This is a producer side process complaining about waits and delays. And so what's happening here, the client is sending its data across the network to the media server. One copy of the BPTM process is receiving it and putting it into shared memory, and the data is coming in faster than the second BPTM process is actually writing it to tape. And so this data piles up in the shared memory buffers until the buffers are full and there's no more room. And at that point, the client can't send any more data until the media server is able to write some of this to tape. And so in the BPBICR log and in the activity monitor, we see again waits and delays being recorded. And again, it is the number of waits that is the significant value. How many times during the backup process did the client have to stop sending data because these shared buffers were full, and there was nowhere to put it. So now that I have this information that I've gathered from the activity monitor or from the log files, of course the next logical question is, what do I do with it? Okay, there were 150 waits during the backup process on the producer side, reported by the BPPICR process. Is that a lot? Well, it's all relative. It's relative to the amount of data I was trying to protect and the amount of time that the backup job ran for. Now, there are always going to be some times during a backup or restore job when there are some delays. It's almost inevitable that there were points where either the producer or the consumer, ran into some difficulties and had to slow down. What I'm looking for are times when the number of waits becomes excessive. And generally speaking, a number above 5% of the time is considered excessive if either the producer or the consumer is reporting delays in excess of 5%. So I'm doing some math, and there's a great example of it on the slide here. So I'm taking a look at the output, which is recorded. Again, it's in the debug logs, but it's also in 7.1 and later in the activity monitor, which is nice. I don't really have to go digging around for it. I can just look at the details of the backup job in the activity monitor. This is a backup job, so BPPICR on the client is the producer, and BPTM, the tape manager on the media server, is the consumer. And what I'm looking to do is take the total number of blocks. Now I get that by taking the data transferred and divide it by the block size. And then I take that number of blocks that I moved, I take the number of waits that were encountered, multiply it by 100, and divide it by the number of blocks. And the output of that's the percentage of the time that we spent waiting, basically doing nothing during the backup job. And so let's take a look. In the slide here, we saw waits on BPPICR on the producer side, 828 waits. We saw waits on the tape manager side, 545 times when it had to stop and wait. And so on the slide here, we took the total amount of data written. We divided it by the block size, which is, by the way, equal to the buffer size being used on the media server that we saw on the previous slides. So sticking with that example, 64K block size that we're using here, divide the amount of data transferred by that's the number of blocks that were transferred. And then taking a look at that compared to the number of waits, we see a significant number of waits on both sides. The producer spent 6.5% of the time not being able to send data. The consumer spent a fair amount of time waiting for data. And so in this case here, where we see waits on both sides, that starts to make us suspicious about the network. Seems like the client wants to send data, the media server wants to receive the data, but they're both sitting around waiting. So, in this case here, we're thinking it's the middleman. Now, another kind of backup job might have given us different results. We might have seen a large number of waits on one side and not so many on the other side. And so you can see where this process is very valuable because I can focus my attention on either the producer side or the consumer side, wherever I'm seeing a large number of waits. This slide is building on the conversation we were having on the previous slide about interpreting these backup waits. And so again, if I see high percentage of the time, lots of waits on the producer and low on the consumer, and we're talking about a backup job, again, that means the client is sitting around waiting a long time. So my problem is somewhere on the storage side, the media server, the SAN, or the storage device itself. If the reverse is true, the producer does not have a lot of waits, 0 or a small percentage, but lots of waits on the consumer side. The media server is spending a lot of time sitting around waiting for more data to come in. Data stream is my problem. In other words, the client system itself or the network between the client system and the media server. I got to look at both. Both are likely causes there. If I see high numbers of waits on both the producer and the consumer, well, then again, like we said before, I start thinking about the link between them is maybe the problem, usually a LAN. And as a guideline, it's when we see a percentage wait time greater than 5% that it really makes us sit up and take notice and say, hey, this is not so great. So there is no one magic number when it comes to the number of waits. For a particular backup job, 500 waits may be a lot. For another backup job, 10,000 waits may be very low. if it's a huge amount of data that we're talking about. It's all relative to the amount of data that we're pushing and the amount of overall time that the backup job is taking. Waits and delays are a problem in any backup environment from the point of view of performance. Obviously, they impact the amount of time it takes us to protect data. They are particularly an issue when we're doing backups to tape because we get into reliability issues as well as performance issues if our tape drive starts shoe shining. And what we mean by that is if data is coming in from the client very slowly, much more slowly than it's being written to tape, then the Netbackup processes have to stop and wait for more data to come in, and the physical tape drive itself has to stop and then back up a little bit and reposition and wait for more data to come in. And so if data is constantly trickling in at a very slow rate, then many times during the backup, the tape drive is stop, back up, write some more, stop, back up, and it's literally dragging the tape across the tape head like a rag shining your shoes, which is why, the industry slang for this is shoe shining. It's no good for the tape cartridge, and it's particularly bad for the tape drive. You'll burn out your drive heads faster if you do a lot of shoe shining. Now, modern tape drives are a little less susceptible to this than older tape drives because they tend to have variable speed motors. So if data is coming in slowly, the tape drive can kind of switch down a gear to help accommodate that. But every tape drive has a minimum data transfer rate, and then typically this is about 40% of its maximum speed. Check the vendor sheet for an exact number. And what that means is the tape drive is saying, if you can't give me data at least that fast, then I'm going to start shoe shining. And so it's important to optimize the data flow to your tape drives for this reason as well, for reliability as well as for performance. And when you consider the write speed of modern tape drives, where these drives can write data in excess of 150 megs per second, you see it's very difficult to keep a tape drive streaming at its maximum speed, as it likes to be, with a data flow from a single client. It's hard to find a production server being backed up that can pump out data quickly enough to keep a modern tape drive busy. For this reason, when dealing with really fast tape drives, it's usually necessary to do disk staging, back up your data to disk and then duplicate it to tape later on, or to use features like multiplexing in Netbackup to keep enough data going to these tape drives to keep them busy so that they're streaming at their maximum speed all the time, because that's what we want. And by the way, that real-world modifier, that 70%, 75% that we talked about earlier in this lesson, does not apply to tape drives. When a vendor gives you a number as a maximum write speed for your tape drive, we want that tape drive streaming at that speed at all times. And we want to do whatever it takes to get enough data going to the tape drive to keep it streaming. Let's say that during our data collection, we're seeing a lot of waits and delays on the consumer's log, meaning that we think the problem is on the client side. So one way to go through and test for client-side bottlenecks, to try to narrow it down to see, is it the host itself, or is it the network, or is it some issue, that's resulting in slow backups? We can establish our client's maximum ability to process backup data. And we do this by using the BPBICR process, the Netbackup client process. As you see on the slide there, we're turning on the detailed debug logs for the BICR process. We're having BICR back up the data, the same data set, associated with the slow-performing backup job. But instead of sending it to the media server like we normally would, we're sending it to dev null in Unix, or the null object in Windows, same thing. Basically, you're just taking all of your data and you're processing it the same way you would during a backup, but you're not actually moving it anywhere, you're just throwing it into a black hole. And this tests your client's ability to process data. You time how long it takes this operation to complete, and that's the fastest rate at which this client will ever be able to process data. So if the numbers you're getting from this test correspond pretty closely to the numbers you're getting during your backup jobs, this is as good as it gets for this client, unless we make some major changes like modifying the application or installing new hardware. On the other hand, if we see that from this testing the client is capable of processing data much faster than the backup job is running, that says to us, all right, it's not the host itself that's the issue, let's look elsewhere for bottlenecks. This slide shows some suggestions for additional bottleneck testing, basically additional ways of trying to narrow things down to pinpoint exactly where my backups are. So for example, if I want to test the connection from the media server to the storage unit, I could try backing up to an alternate storage unit on the same media server. If I want to test my network throughput between the client and the media server, I could try moving some data outside of Netbackup, for example by using FTP, and getting a good idea of what the maximum transfer rate on the link is. If I think maybe the storage unit itself is the bottleneck, then I could switch to backing up to another storage unit, or I could back up to a null storage unit. Now there's details on how to configure null storage units in the Netbackup documentation, and this is similar to the client-side test we were doing on the previous slide. You send a lot of data to the media server processes it, and instead of sending it to an actual device, it just sends it nowhere, throws it into a black hole. Null storage units can be very useful for performance testing, but do be very careful with them. Try to use them only in a QA environment, or if it's in production, delete them as soon as you're done with your testing. Remember the null storage unit is basically a big garbage can that goes nowhere. So you don't really want these objects lingering in your production environment just because they can cause data loss with improper configuration. And then finally, if I want to see if a media server or storage unit is optimally handling the number of I/O streams, then I adjust the number of streams to try to see what the point is at which I see contention. When I'm doing testing for bottlenecks, for my initial baseline testing, that process of trying to see in general how fast data moves across my components, it's best to use large, simple, identical files. However, when it comes to identifying bottlenecks, it's best to use data that best simulates the actual production data being protected. So the number one most useful thing to do would be to use the actual data, or if you're in a QA environment, to see if you can arrange to have a snapshot of the actual production data available. That'll give the most accurate results. If something like that is not available, then I'll want to use some kind of a stimulator to generate sample data that is similar in characteristic to the data being protected. Now there are tools outside of Netbackup that can do that. There's also the GenData directive within Netbackup that's available for Unix and Linux clients. And that the GenData directive can be used to generate a sample workload, which is helpful for bottleneck testing. This is the addressing bottlenecks topic. The next step, after identifying where my bottlenecks are, is addressing and attempting to resolve them. This slide shows a number of different areas in which you can have bottlenecks. For example, storage-related factors, application-related factors, or Netbackup-related factors. For each of these categories of client performance issues, here are some recommended solutions to consider. For storage-related problems on the client, we can look to address disk or network bottlenecks, or to see if there's ways to improve file system performance through maintenance or defragmentation. Is it possible to introduce snapshots into the backups? Sometimes that can improve performance. If we're talking about a large file system with many small files in it, the Netbackup Flash Backup option might be a possibility, something we discuss in a basic admin class. Take a raw partition backup of the entire volume and then map it so you have the ability to extract individual files from it. That might give you better performance. For application-related issues, the use of Netbackup agents rather than old-school dump and sweep data protection strategies will generally give better performance. Also, the Netbackup accelerator feature can help a lot, particularly when we're talking about virtualized applications. When it comes back to Netbackup related issues, turn off detailed debug nogs when they're not needed, because they're just generating lots of extra I/O. Make sure your notification scripts are working correctly if you're using any of them on the client, because they'll eat up more time if they're improperly configured. Make sure with deduplication that any compression or encryption that's taking place is being done by the dedupe engine and not by an outside source. And again, consider the use of Netbackup Accelerator, which can greatly improve backup performance, particularly for full backups. This slide shows some possible bottlenecks that you might see on the storage side. storage-related factors such as slow tape drives or outdated firmware, data stream-related factors such as a slow or unreliable network, or Netbackup-related factors such as non-optimal buffer settings or server-side deduplication. For each of these possible storage-side bottlenecks, here are some recommended solutions that we can try. For storage-related issues, we can try upgrading to faster hardware or using disk staging, which, like we mentioned before, is strongly recommended when working with modern tape drives. For data stream-related solutions, we can take a look at the use of multiple data streams and multiplexing to increase the number of concurrent jobs running and hopefully improve overall backup performance. We can also look at different ways of doing LAN-free backups in Netbackup, such as SAN media servers or the SAN client feature. On the Netbackup side, again, detailed debugging logs should be disabled when they're not needed for troubleshooting. Having a lot of logs on at a high verbosity will generate a lot of extra I/O on the servers. We can look at doing buffer tuning to optimize the data flow, something we'll discuss later in this lesson. And we can look at other Netbackup features, for example, load balancing media servers with deduplication, switching to client-side dedupe instead of server-side dedupe if it seems like my media servers are struggling, with the amount of fingerprinting that they have to do, or the use of Netbackup Accelerator, which is a terrific way to improve performance for full backups. This slide lists some references and links for the discussed performance solutions. The Netbackup Planning and Performance Tuning Guide is an invaluable resource for every step of the performance tuning process and contains a wealth of information, some of which is covered in this lesson, but a lot of which is discussed in far more detail in this guide. Definitely a must-read for anyone doing performance tuning for Netbackup. And then there's some more specific information points available here, for example, for file system defragmentation, or for the use of snapshots and flash backup in your backup process. When searching for bottlenecks, always remember to consider device drivers and firmware levels, because in a big enterprise environment when we're swapping out failed components, it's easy for the firmware of different components to get out of sync with each other. If we have a particular component out there that has a way old version of firmware, it might not have the latest performance enhancements, and it might be dragging down overall performance. This slide over here kind of shows an example of doing a firmware audit where we trace the data path from the clients to the media servers and identified all the components we were passing through and checked their firmware version. And in many cases, the ones highlighted in red text on the slide here, we found some firmware that was pretty far out of date, where updating it to the latest version might result in better performance. When we were discussing different strategies for keeping fast tape drives busy, we mentioned two of the most common strategies are disk staging and multiplexing. They're both ways to feed more data to your tape drives. Between the two, disk staging is definitely the preferable option. Do your backup initially to disk and then duplicate it later on to tape. But that's not always possible. We don't always have the amount of disk space available to buffer everything on disk before it goes to tape. So for clients who have to be backed up directly to tape, we can look towards multiplexing to improve overall throughput and tape efficiency. Multiplexing is discussed in detail in the basic administration course, but we just wanted to give you a few more reminders about using multiplexing. In particular, remember that the combining multiple streams onto one tape drive simultaneously can improve overall throughput, but it's additional work that the media server is doing during the backup window, and there's the potential for complications during restores if you're doing individual file restore from large images which have lots of multiplexing done upon them. So avoid configuring unnecessarily high multiplex values. Generally speaking, once you start getting above 10, we start to consider that kind of a high multiplex value. The Netbackup will allow you to set it up to 32, but 32 is a lot. Honestly, if you ever find yourself considering multiplexing more than, say, 15 or so streams together to keep a tape drive busy, you really should be looking at disk staging as a better solution. This is the Tuning Netbackup Buffers topic. Earlier in the lesson, when we were discussing the identification of bottlenecks, we discussed how the data flow from the client goes to the media server and passes through shared memory before it is finally written to the backup device. The amount of shared memory that's used for these buffers is tunable, and it can improve backup performance. In particular, backups to tape will almost always benefit from buffer tuning. The process of buffer tuning should be cautious and methodical. And so here's some high-level suggestions on this slide as we begin the process. First of all, to make sure we have all the information on hand, that we have actual numbers about the data speed from Netbackup reports or from other sources, that we have information about the devices that I'm using. For example, the maximum recommended block size for my tape drives, if we're talking about changing the buffers to tape. And during the buffer tuning process, make small changes, one at a time, document the change you've made, and test thoroughly before and after each change. Test your backups and test your restores. Make absolutely sure that none of the changes you've made during the buffer tuning process are going to in any way compromise your ability to recover data. The shared memory used on the media server during backups is comprised of a number of buffers of a certain size. So in this slide here, the example, it looks like we have 8 buffers, 64 kilobytes in size. Both of those characteristics are tunable, the size of the buffer and the number of buffers. And here's how you want to think about that. The size of the buffer translates into the block size on tape or on disk, because Netbackup always writes a full buffer at a time when it does I/O transactions to disk or to tape. So for example, in a backup to tape, your buffer size is your block size on tape. So that means that the process of tuning buffer size is pretty straightforward. Identify the recommended block size on tape, set the buffer size to that value, and you're set. Never exceed the maximum recommended block size that the vendor recommends for a particular tape device. Doing so can result in write errors, or in really bad cases, the ability to write data that may not be recoverable later. Now, when it comes to the number of data buffers, this is a little bit less straightforward. There's usually no fixed limit unless we start to approach the maximum limit of shared memory that the operating system supports. And so what we're looking to do here is adjust the size to the most optimum value for the device that I'm backing up to. And if I think that I can still get benefits by increasing shared memory, double the amount of buffers I have, and continue doing this for as long as I continue to see measurable, real-world performance gains. Remember, when I'm doing this, that I sort of have two things I'm looking at. I want to see the number of waits and delays in the logs go down, but I also want to see the backup run faster. And you will reach a point during this process where you're kind of reaching the point of diminishing returns, where allocating more RAM to shared memory buffers for Netbackup is not really causing a tremendous increase in performance. What we want to do here is we want to identify the sweet spot, where the amount of increased memory we're willing to allocate to this gives us the best reward. So as we see on the slide here, size data buffers for tape is set to the optimum block size for a tape device. For a disk device, a lot of times making it equal to the stripe unit size of a rated up disk will result in optimum data throughput. When it comes to the number of data buffers, I'm increasing them continuously for as long as I see performance gains. Remembering that the size of my buffers times the number of buffers is how much shared memory is being exclusively allocated to Netbackup per backup job. And so I also want to make sure as part of this process that I don't allocate so much RAM to shared buffers that the media server becomes starved for memory, for other uses. Generally speaking, media servers these days come with a generous enough amount of memory that I won't normally see a problem there, but it's something to keep in mind. How many simultaneous jobs will this media server be running at any particular point in time? Some buffer tuning settings will be limited by the operating system's restrictions. And so we see the slide here on Unix, the maximum data buffer size is typically limited by the shared memory kernel parameters. On Windows, Windows has limits on how high you can set either tape or network buffer size. The slide directs you towards tech notes with more detail if you're concerned that during your buffer tuning process you may be approaching any of these limits. This is the Tuning Netbackup Deduplication topic. When doing performance tuning, where the use of deduplicated disk is involved, here's some recommendations for getting the most performance possible out of your dedupe solution. When it comes to compression and encryption, if either of those features is required, and a lot of times it may be, for example, if you're doing client dedupe of a remote client across a WAN, make sure that compression and encryption are done by the dedupe engine itself, and that they are not done before deduplication. Compression and encryption are poison to dedupe. If you encrypt your data and then send encrypted data to the dedupe engine, you're going to be getting 0% dedupe rates. What you want to do is deduplicate the data first, and then have the dedupe engine encrypt the data so that you still get encrypted data going in flight, but the benefits of deduplication are applied before the compression or the encryption. In Netbackup MSDP pools and Netbackup appliances, compression is enabled by default. Encryption is not enabled by default, but is available. When we talk about virtual machines backups to a dedupe disk, generally speaking, doing target dedupe gets you the best performance there, and always make sure to use the enable file recovery from VM backup option so that Netbackup actually analyzes the files inside the VMDK or VHD file and not just a big blob of data. You can consider, in the case of my WAN client that I was talking about before, the use of a deduplication cache. In other words, seeding the dedupe pool prior to the first backup of the remote client. The first backup of any server, the very first time you protect it, usually does not result in particularly good dedupe rates. It's possible to seed a dedupe pool with a full backup of a client, and to do that by physically shipping, the data from one site to another, so that you don't have to push a full backup of the server across the WAN. Also, make sure I'm getting the most benefit out of the stream handlers that Netbackup provides. Stream handlers process data as it's being backed up and are sometimes able to improve deduplication rates. Stream handlers are specific to specific data types, and they happen during the backup process. So make sure your initial backup destination is one that supports deduplication, and then if you want to duplicate it later on to a non-dedupe disk or to do a tape out, that's fine. But make the dedupe disk the initial target for best dedupe rates. This is the Using Network Resiliency topic. Network resiliency is a feature in Netbackup that's designed to improve the reliability of backups across a shaky network connection. So usually we're talking about a WAN here, although it would apply to a local network as well if you had a LAN with a lot of latency or just overall poor quality. Without the network resiliency feature, if the network fails during a Netbackup operation, the job fails, and usually you have to manually restart it or wait for a retry. With the network resiliency feature on, if the network connection fails during an operation, Netbackup can recover the operation without intervention. Basically, it can reestablish the connection without administrator assistance, and the backup job runs successfully. This can be a great time saver, again, especially when you're dealing with high latency or shaky WANs. Network resiliency works for backups and restores, and it is specifically a feature that works between the media server and the client. It is not used, for example, for communication between media servers. It supports most backup types, such as standard backups or backups going to MSDP pools. The only types of backup it really doesn't support are those going to the old PureDisk pools, anything using the PDDO option. And then just note that the network resiliency feature uses the VNet-D port instead of the PBX port, which is used for all other client backup operations. Resilient network settings must be set using the master server host properties. In the Resilient Network tab, you can configure which networks will use the network resiliency feature, and you can do this by short or fully qualified domain name, or you can do this by IP address using either IPv4 or IPv6 format. You can do specific IP addresses for specific hosts, or you can do entire subnets, as shown on the slide and in the example. Resilient network settings can also be viewed from the media server host properties, although they cannot be configured from here. In the same manner, resilient networks can be viewed but not modified from a client's host properties. To verify that resilient network connections are being used during a particular backup, examine the detailed status from the activity monitor for that backup job and look for the line Using Resilient Connections. As discussed previously, resilient networks are a feature that functions between clients and media servers. Supported deployments include backing up to either tape, basic disk, or advanced disk, or to a deduplication media server, an MSDP, or a Netbackup appliance, and that could be using either target or client-side dedupe. Network resiliency does not support communication between Netbackup servers, from media server to media server, or from media server to master. And so you see what's happening here. A client is being backed up to a local media server in a remote office, and then there's a duplication taking place between the remote office and the main data center. That opdupe going across the WAN is not getting the benefits of network resiliency. This slide shows some additional unsupported deployments. So when using PDDO to a classic pure disk deduplication pool or to a Netbackup 5000 series appliance, network resiliency is not supported. This slide shows some other considerations when it comes to network resiliency. Be careful about setting excessively high debug levels on the NBRTND process, which is the one that's used for resilient networks, because it can cause excessive amounts of logging. Remember that network resiliency does not include encryption. Now, encryption is still possible using any of the encryption settings that Netbackup supports, but just remember it's not something that's automatic and built into the resiliency feature, even though it is a feature, that targets WAN, and encryption is often desired across a WAN. Also remember, like we've mentioned a couple times already, the network resiliency feature is between a client and a media server. It is not used or not helpful between media servers or between media and master servers. There are other types of WAN optimizations that are available. For example, Netbackup appliances include built-in WAN optimization that will help with duplication and replication, but that's not part of this feature. Also, the NBRNTD process uses the VNetD port 13724, so we're not using any additional ports here. Most Netbackup environments will have VNetD and PBX ports open. In this lesson, we learned about the performance tuning process for Netbackup. We learned how to use various tools to identify and correct bottlenecks. We learned about Netbackup features that can improve performance. And we learned how network resiliency can help backups in latent network situations. This concludes Lesson 2.